Hello, I'm Greg Yeric from ARM Research, and I'm honored to be giving a SKYTALK at this year's DAC. But I'm even more honored that you stopped by to watch, because if your year has been anything like mine, it's involved a lot more screen time than I ever would have imagined. Well, here's where we should have been meeting. I'm sorry it's not in person. I actually know the Moscone Center much better for semicon. I've been to many semicons. And when I was invited to give this talk, of course, semicon and DAC were going to co-locate, and I was particularly excited because bridging these two fields is very much my line of interest. And I put these themes into the talk. You'll see these throughout the talk. And this being a SKYTALK, I wanted to challenge myself and look at our industry 10 years from now, around 2030, and what could be in that time frame. And particularly 2030 is interesting for me because 5 years ago, for the 50th anniversary of Moore's Law, I predicted that Moore's Law would end in 2029, humorously, of course, from this extrapolation. But there is very good debate going on about when Moore's Law will end, now even how you define Moore's Law. And that particular debate is important given the progress that we've made over this course of the last 55 years. From 6 transistor chips that got us to the moon to 68,000 transistor chips that ushered in the dawn of the PC connected internet, to now 30 billion transistors that put us firmly in place of a new data economy. But with this amazing progress comes global responsibility. The systems that we are enabling are using an increasingly large slice of the world's energy output. And of course, from a sustainability perspective, if anything, this is a major concern. And we continue to grow this. As you can see, the projections continue to grow for electronics. Now, even today, the volume of information is amazing that we're putting up onto the internet. No matter how trivial you think this may be, this data has to go somewhere. It has to be uploaded, analyzed in cases, viewed. This all takes energy, and we're running out of energy. Now, these cat videos have to go somewhere. You see this in the growth of these hyperscale data centers, growing very rapidly right now, as well as the infrastructure to connect. And 5G, of course, very much anticipated. Importantly, 5G will move us from a paradigm of a person-machine connectivity to machine-to-machine being the majority in just a few years. And that's why you see these energy forecasts having this inflection point right around that time, from a consumer device dominated perspective to one that's dominated by networks and data centers. So let's talk about what we can do in our industry towards 2030 to make a more sustainable future. Now, power and delay are obvious topics. I'd like to get to those, but I'd like to start with cost. Cost, of course, we can make the lowest power, fastest machines, but if no one can afford them, that is a problem. And I've been tricking you with this plot. It's in the form you'd expect in transistors per chip or per square millimeter. But these data are actually in dollars. And they represent the purchase price of the tools required over Moore's Law to do the patterning. Now, EUV has come in at over the $100 million mark. It's doing a fantastic job, from what I understand, in 7 and 5 nanometers. But we actually have another data point. We know that, as amazing as EUV is, that by mid-decade, we're probably going to need a high numerical aperture upgrade to the EUV systems. I'm showing below me a test chamber for some of these new mirrors by Zeiss. This is very much high-tech applications. The red outline you see here in this graph is the current EUV systems. They themselves require 3 Boeing 737s to transport. And that's just in the fab level. Below the fab is a laser that is more powerful by energy than the test system that the US Navy is using to shoot down missiles. So a lot of extreme tech here. Amazingly, $255 million actually comes in under that trend line, so it's a bargain. But if you take that trend line out, you're looking at spending more than $1 billion per tool to do what we need in 2030, whatever that might be. So what options might we have? To give you some perspective, current EUV tools push the equivalent of 30 million UHD television sets worth of information onto each wafer. So extrapolate towards 2030 and you're asking a lot for any top-down patterning technology. Now I've listed here some of the candidates. I'm not aware of any of these having a defined roadmap to 2030. I'm not aware of anything. There's been many attempts at the E-beam area. The one I know about that's still continuing is multi-beam. They claim to be still pursuing a CMOS manufacturing angle. I'm really impressed with what Canon's done with nano imprint. Not sure it can get there either. Fundamentally, if we look at what we would really need, we want to break this top-down bottleneck and build from the bottom up. And that's the topic of self-assembly. Now, self-assembly through DNA started in the late 90s. It continued very importantly in 2006. Paul Rothman showed a technology where he could add binding locations to DNA where small pieces called staples would attach and then reattach to link and form the DNA into specific shapes. Here are some of the shapes Rothman made in 2006. Smiley faces, stars, and to give you a perspective on dimension, our upcoming 3 nanometer node will be lucky to put 2 gate lines down where he's been doing smiley faces and stars for the last over a decade. And the comparison is actually even less fair than that because in that area, he can attach binding locations for other molecules within about a 5 nanometer resolution. Now, sprinkling a bunch of these on your wafer probably isn't going to help you much. And that's where Lulu Chen's group came in a fractal assembly of this DNA origami field. Now, fractals reuse constructs across size domains, and that's exactly what they did here. They took a test tube that would form one of Rothman's tiles. They ordered 3 more, programmed the edges so that they would only bind in one way, and then replicated that. So with 4 test tubes, they got a 2x2 matrix. They repeat that again to get a 4x4, repeated again to get an 8x8. And when they were done, they had made the world's smallest Mona Lisa, about 700 nanometers in size. Now, our $255 million high NA EUV tools won't be able to make that. Who did make it were a couple of postdocs, an Excel spreadsheet, and $20 worth of DNA. And they actually get about 1 billion copies per test tube, so you're looking at a 20 nanocent Mona Lisa. Now, to give you perspective in size, you could take a 7 nanometer chip that is, say, 20 millimeters by 20 millimeters, and at the scale of the DNA folding, you could make that about 2 millimeters by 2 millimeters. Or, say, keep the same size and put 6,000 cores down. So, throughout this long, impressive history of Moore's Law, Richard Feynman is still right after this time. There is room at the bottom, at the molecular level. Now, DNA origami doesn't have to be 2D. It can fold into 3D shapes. If you need a dodecahedron, no problem. Here on the right, I've got an example from Harvard where they're basically making voxels programmable to whatever shape you need. And if you do 3D, you could take that 2 millimeter example I showed and fold it into, say, a 130 micron cube. Now, that is important actually for another part of the data economy story, and that, of course, is machine learning. It's hard to believe that just back in 2012 was when the AlexNet DNN won the ImageNet competition. So the first time a deep neural network had won that competition. Just 3 years later, ResNet became more accurate than the human benchmark. What you're doing in machine learning is you're trading off programming complexity for training. In our topic here, energy, took about 70 kilowatt hours to train ResNet. Then when things took off and you had real companies applying real big budgets of hardware to real big problems, of course, the very common example here is the AlphaGo Zero, $25 million in hardware. That required 216 megawatt hours to train. So to put that number in perspective, I could take a Tesla Model S and I could drive it from Cambridge to Lisbon to Rome to Warsaw back to Cambridge. And I could do that another 146 more times. So this is a non-sustainable roadmap, of course. And the OpenAI gave a good example in this plot here where they showed the progress of machine learning and the energy required to do the training. And ignoring the fact that these data points are actually accelerating faster than that trend line, if you extrapolate that out, you're talking about a training budget of 280 yottaflop days to 2030 timeframe. At the same time, this is roughly how Moore's law progress would have you go. So this is certainly on a unsustainable path if we can't get the machine learning to be more efficient. Now, we are making great progress in the machine learning systems. You look at the number of neurons and how it compares to the biological equivalent. But of course, you compare, the fish to the Pohiki Springs hardware, and you're seeing that, this is very inefficient compared to the biological equivalent. And one of the reasons that we're so inefficient is the connectome that is the true neuromorphic. So in true neuromorphic systems, you have at least 100 and up to 100,000 inputs per neuron. We just can't get there with what we're doing in our current hardware. So that's part of the challenge is, how do we make hardware that can fundamentally push this as far as we want it to go? And we're very limited by the two-dimensional nature of putting down contacts and wires to transistors. And that's why something like molecular self-assembly, in my opinion, provides a jump possibly to get us to where we need to go. Now, highly speculative. All patterning techniques that I know of that are pointed towards 2030 are speculative. There's one other reason why I think that the molecular assembly is something to pay attention to is it doesn't need us to continue. Now, in the semiconductor industry, we spend a lot of money on R&D, but we are the number 2 industry. The number 1 is healthcare. And in the healthcare industry, they are currently curing cancer in mice using DNA origami. So that's one reason that I think technologies that such as this that can benefit multiple industries, and of course doesn't even need us to continue, it's doing quite well in healthcare, we should be paying attention to it. Now, to move to energy and delay scaling and looking at this path towards 2030, we know, of course, down in our circuit level that the switching energy has been extremely challenged in terms of scaling. Looking at the forecast from ITRS, this is going to continue. This slowness from our expectation is limiting system performance. Lots of topics, I'm sure, at DAC in the past that you've seen in terms of dark silicon and what have you. But this is a fundamental problem that we have pushing CMOS down this far. Professor Philip Wong, who I hope you caught his keynote. Of course, I'm recording this early. Don't know what he said. But I always come back to his paper from 2009 where he showed just the fundamental geometrical challenges of scaling CMOS into the nanometer regime. You have a fundamental intrinsic capacitance that scales. That's the brown part of these bars that you see. But there's a lot of non-scaling parasitics, and you reach a point of diminishing returns. Now, normally when a challenge is put forth, like Professor Wong did here, the resourcefulness of the semiconductor industry kicks in and we solve it. In this case, if you look at 7 nanometer, 5 nanometer CMOS, in fact, the capacitance of the intrinsic transistor is less than the rest of the parasitics. It's just a geometrical challenge. And to add insult to injury, the resistance of the channel is less than the resistance of the parasitics responsible, for instance, the contacts and what have you. So around about the time that the system level people had to revise their law, Kumi's law, is when Professor Wong pointed out that we really have some fundamental problems and they're hard to get around. Math is hard to get around. And we're not helping ourselves with the current and future generations of FinFET, even leading up to the gate all-around stacked nanosheets. We're getting a lot more current per micron, but we're certainly not helping ourselves in terms of parasitic capacitance and what have you. So let's step back. We're talking about a decade from now. What would we ideally like? Well, there is a path towards stacked CMOS that isn't going to fundamentally change this math. What we fundamentally like is the 2D transistor, something that is so flat we can drop the aspect ratio of the gate and the contact. And of course, this is ideal. We don't know of one. In fact, we all know of the hype of graphene. Without a band gap, it really couldn't live up to the hype in the semiconductor switch field. Of course, graphene is going to change our lives in other ways. But it did unlock the Pandora's box of two-dimensional materials. And there are many actually candidates now, and there's something important with the term many. Here's one paper that identified 51 new 2D semiconductor material candidates. Here's another paper that identified 57 more quaternary. So these are so complicated, I don't think you're going to get there with Scotch tape like graphene did. And these are showing up in bunches all of a sudden. So here's the two papers I referenced. They are not Scotch taping. They are computing. They're using a technique that was recognized in the 1998 Nobel Prize for Chemistry. It's using the term DFT very differently than I'm sure you're used to in the DAC world. But basically, the computing power we've enabled through Moore's Law has become formidable enough that allows the chemists to do what they call these ab initio calculations, not having to do simplifying fudge factors and really getting some accurate material simulation. Now, some of the simulation points in the paper per point take days of computation time. So as we make more powerful computing systems, we can expect to enable the continued advancement of this field and hopefully reap the benefits by 2030 when we'd probably like to have them. So we look at this timeline. This industry has been extremely resourceful, literally squeezing performance out of MOSFETs. And there may be a roadmap to 3D that allows us to get to dimensionally where we want to go. That's 6 times smaller in 2030 than where we are now in production. But really from a power and delay standpoint, it looks difficult to get where we'd want to go with CMOS. So that's why I'm particularly excited about this field, new material development. Not just in 2D, there are many technologies that look potentially interesting, but many of them don't behave anything like CMOS, and they're very difficult to understand where they might fit in terms of competing with CMOS and bettering it for certain applications and what have you. And I want to take one example here, the transmonics. Transmons being related to the qubits that you make for quantum computing with Josephson junctions. But you can make conventional switches with these Josephson junctions as well with this effect. That's this field of superconducting electronics, the single flux quantum effect. That allows you to make logic signals of these little millivolt burps, and they're going extremely fast, with the caveat that this requires cryogenic cooling. It's not going to show up in a phone, but there are people that think that a data center justification is here for looking into this field. However, these don't behave like CMOS. They're very fundamentally different. These are inductors. That's not a capacitive effect. That really challenges our standard cell paradigm. The wires are superconducting. They don't tolerate fan out like a copper wire. So there are fundamental ways that we need to re-examine what we're doing. And a company like mine, we would prefer a nice design flow ready to go so we can do, because we need to percolate this up to the system level. That's how fundamentally different this is. And at the same time, we can't expect the EDA industry to throw out EDA flows for every speculative new technology that comes along. So this is a chicken and egg problem that I expect to occur more and more as we start to see more of these fundamentally different technologies. In this case, IARPA stepped in and they funded an EDA, or are funding, this is an ongoing project, EDA infrastructure for this technology. And when this is ready, the goal would be that an ARM research group, for instance, could come in and really look at this from a data center perspective at the system level and really work through some of the issues. So as I mentioned, this will be an important dynamic going forward. many of these new materials / devices / even physics upgrades are going to fall in the same chicken and egg problem. So they look so different than CMOS that they're not going to be useful to benchmark in an existing design flow. And there are only so many dollars from IRPA to go around. So this design EDA conundrum is part of a broader topic that's famously been discussed, I know, in the US government for years, that is often referred to as this lab to fab gap, sometimes even the valley of death. So we have a pipeline of interesting technologies. Some of the things I highlighted in earlier come out of SRC or JUMP, for instance. We have some limited application in the gap area. I think ERI is doing a good job in some aspects. IMEC is a way that the private sector is pooling pre-competitive money to address this. But there's going to be a lot of these challenges, and I think this is going to be a key issue, especially given that our industry, semiconductors, that private sector bump is moving out and increasing the gap. I mean, the scale and precision required to move down the leading edge CMOS nodes is really going to expand this gap. You're asking a lot of any new fundamentally different technology to prove itself to the private sector. This is going to actually increase rather than even stay the same. And of course, you need to increase spending as you go across this timeline to examine a technology as a potential augmentation, for instance, to some aspect of CMOS. You, at this point, really need to be down in the nanometer dimension, have really good statistics, show how it can be manufactured on 300 millimeter wafer tools. This is a lot to ask, especially given that we're not talking about one or two, we're talking about a handful of these that are really going to need to make this jump to get us into the 2030s, in my opinion. Now, in the US at least, there's a renewed interest from the government to spend in the semiconductor manufacturing area. We see some bills out of Congress here. I'm showing a couple. A lot of this is earmarked towards conventional manufacturing facilities, but I sincerely hope, and I believe in some of the wording of the bills, that there will be some significant resources applied towards this gap, this lab to fab gap. In fact, I think it would be a good idea to put embodiments into that gap, such as like a national nanoelectronics lab. Because that's where we have a lot of problems moving from, say, the academic research to something that is proven to the level that's required for the private sector, is this need to get statistics on relevant constructions at relevant dimensions. And that's very difficult to do in this distributed university research environment. And that's where a lot of these are going to hit a snag and have in the past. Now at ARM, we are obviously working in this gap area often, looking at new promising technologies, trying to figure out how to rationalize them in a meaningful way for, in our case, at the architecture level, system level. And I want to give you two examples that work in this theme that I'm talking about today. The first one involves a couple of strange bedfellows, ARM and Unilever, computer chips and deodorant. But it turns out there are people at Unilever that are the world experts at sniffing armpits and telling you how well your deodorant is doing. And in this work from home era, it would be really good if your family members didn't have to point out to you that you've been wearing your shirt too long. Now, with a low-cost material from the University of Manchester, some innovative manufacturing from Pragmatic, we at ARM are endeavoring to make AI applications that allow flexible chips to be sewn into your shirt and help your family members with this vexing problem. Now, of course, this is a funny example, but I use it because it embodies this vertical integration. You might call it materials to systems, you might call it atoms to applications, but when you have a new application that's embodied by some kind of new device, you really have to rationalize through the stack. In this case, it's not particularly disruptive. Of course, machine learning is compared to standard digital logic. But in general, the devices are still transistors. It's not that disruptive from the stack perspective. But this is an example of the kind of coordinated effort top to bottom that will be required with some of the more disruptive things that we see coming along in the pipeline. Now, the Moore's law discussion frequently hyper-focuses on logic transistors. I'm not going to get into analog, and I would love to get into the wiring, which is over half the problem. But also the memory devices. The memory roadmap is particularly frightening almost to those of us in the system level across the board, NAND, DRAM, SRAM. They are limiting what we're planning for our system roadmaps in some cases compared to the kind of scaling that we had been used to in the past. SRAM, embedded SRAM in particular, the bit cell area has been slowing off of Moore's law, and looks like beyond 5 nanometers, that's just going to get worse. And that does, of course, obviously would limit architectures in the CPU space, for instance. There are several promising non-volatile memory technologies. None of them appear to be able to present a gigantic and prolonged step improvement to make up for that gap. I may be proven wrong, but we do monitor that space. Obviously, that's important to us. And in the course of that, we did identify one technology that had this exact, lab to fab conundrum it was facing, and it looked promising enough, potentially differentiated from other things we saw, that at ARM Research we signed up to go ahead and help the lab to fab issue. So here you have devices from Symmetrics that are manufactured at the lab in the University of Colorado Springs, and our job, you see the cross section at the top, was to demonstrate them on 300 millimeter wafers at relevant dimensions, and we've started to do that successfully. This work was funded in part by the ERI. I showed that icon on the last slide, and the DARPA ERI program has the same general philosophy. They are designated as these pillars: materials, architectures, and designs. You need all the pillars for a stable future in electronic capability. They do, in the ERI nomenclature, call some of their investments page 3 investments. That refers to the page 3 of Moore's paper, where he did presciently look into the future and predicted that simple transistor scaling may not be enough. There are things we're going to need to do that are in addition to that. So these page 3 investments through the ERI, I did see, by the way, in some of those bills, there is money specifically earmarked to continue the ERI. Now, the program that we were partially funded in was specifically looking at beyond von Neumann applications. And in that case, for us, in a memory element, resistive memory element, that means multi-level cell. So that's what we've been busy with, is proving multi-level cell capability for analog neuromorphic use case of this memory. Now, ARM, being one of these private sector companies that likes to make profits, memory market is important, and we are continuing that program separately as well, making good progress in this exact lab to fab scenario that I described before. Can we show that it's a memory in relevant dimensions with relevant parameters? And that's still looking promising as well. Now, the correlated electrons that we call CeRAM come from the theory from Mott, for which he won a Nobel Prize back in the 1940s. And in fact, the correlated electron term comes from his paper. This is a new type of switch. And so while we're pursuing conventional memory applications, it presents other capabilities that may open up additional applications and uses. One of which is these orbital switches are relatively temperature independent. Our test equipment is limited to 400 C on the high side and 1.8 Kelvin on the low side, but we're showing that the device does natively sweep across this temperature domain, which we have never seen before. And that may open up memory for a wide range of things that don't have necessarily a good memory in your standard CMOS operating window, or outside of that, I should say. And being a new device, and of course, being a topic since before Moore's Law, there's been a lot of work in the potential of something like MOT switches, in addition to memory devices, a lot of interesting research in terms of sensors, photonics, and then mentioning photonics, one particular field that I'm excited about that for time purposes I didn't speak about today is this metamaterial device. And that basically, metamaterials are materials, you're using electronic or photonic properties of materials, but also shrinking them to the dimensions that are relevant to the wavelength of the particle. And so in case of photons, we can easily get there with existing semiconductor patterning. And that opens up potentially some really interesting photonic interactions, for instance. Very excited about this field. Specifically also, it requires the combined fields that DAC and semicon represent. It's manufacturing capability and the new paradigms in devices that are going to require some work in the EDA area to help us rationalize these as system components. Now back to our memory example. We are facing this gap where, for instance, if we want to justify MLC capability for a modern CMOS node, that requires a lot of wafers and a lot of statistics and a lot of experience in terms of how you specifically deposit, etch, manufacture, integrate this device, and what explicitly what variation components you can control and to what level. So we're facing this gap in this particular project, of course. The story of this is not finished. It's still being written. It may not only include ARM going forward because obviously we don't run a factory, but we have gotten it to that point and are excited about this as an example of some of these new device concepts that are in the stables in the research labs around the world. So here I am back to pretending I'm in San Francisco. I took this picture, by the way. It's from the bar at the top of the Hilton in San Francisco. And to summarize my talk, I personally think it's an exciting time, this period from now till 2030, where we will have viable new, call them post-Moore, beyond CMOS options. Those of us in the EDA and combined manufacturing fields are going to have to get together and figure this stuff out in terms of what can make the jump across this lab to fab gap. Now, to do that, this vertical structure I mentioned, materials, systems, atoms, applications, we're going to see this as a challenge to the industry because each one of these is a new endeavor in terms of design studies, EDA capabilities, understanding how to make these things. But that's why I was initially very excited about the combination of the two conferences, and I remain excited should this continue for this particular reason. The DAC semicon represents somewhat of the vertical integration that is going to be required to make progress as we would prefer through 2030 and beyond. Now, if you're participating in the virtual DAC event, I've left room for questions. If you aren't, there's my email. Feel free to contact me with any questions. And again, thanks for listening wherever you are today.